Hi everyone, welcome to the Threat Briefing podcast by Vectra AI, where we explore how modern attackers are targeting modern networks and what defenders can do about it. I am Lucie, and today we're kicking off a new series focused on threats against generative AI systems. In this episode, we're zooming in on the model layer, how threat actors are manipulating LLMs to leak sensitive data, bypass guardrails, and undermine enterprise systems. Joining me today is Zack, one of our lead data scientists here at Vectra AI. Hi, Zack. Thanks for being here.
Hi, Lucie. Thanks for having me.
So let's dive in. Here's my first question. What are some ways attackers manipulate model behavior during inference, particularly through prompt injection?
Yeah, that's a good question. Prompt injection is really the big way here. I mean, all of the large language models that we're talking about and their offshoots, the way that their users are interacting with them, both benign and malicious users, is through the prompt. So they're the kind of classic prompt injection approaches that are out there and have been out there for as long as LLMs have been a thing. There's been a lot of really good research into ways of jailbreaking language models to try and get them to bypass their own built-in guardrails. One of the things that I find really interesting, though, is less about manipulating model behavior per se and more about manipulating system behavior. So one of the really interesting attacks that has been researched and talked a lot about lately. It was research done by AIM Security, and they're calling this Echo Leak. And it is, technically a prompt injection attack, but what makes this special is that it is using a different pathway than we've seen before. So this Echo Leak attack that they researched and published on is specifically targeting M365 Copilot. And one of the unique things here is that there are multiple ways in M365 Copilot to contribute to the prompt, the context essentially that the model is using when responding to a new prompt, including through a user's emails. So in this Echo Leak attack, what they basically found is by sending an email, all they have to do as part of this attack is send an email to a user for which M365 Copilot is monitoring that user's inbox. Now they've essentially injected their malicious prompt into the user's context without the user even being aware of it. And through this attack, they're able to then exfiltrate data based on what the benign, the intended user is doing. So they call this a zero-click AI vulnerability. It's something that fortunately has been patched at this point, but conveys a kind of broader consideration when designing AI systems. We tend to think of a prompt or a chain of prompts as being kind of a single unbroken chain, and we start with whatever the model's system prompt is, and then there's kind of one stream of information that's being added to it, and that's the hands-on keyboard user who's asking things of the LLM and getting responses back. And that's really not the world that we're living in anymore. We have more sophisticated AI agents that are pulling information into their context, yes, from kind of the user's chat thread, essentially, but also from other sources that in some cases the user may not even know about or be cognizant of. So you can consider this a kind of poisoning attack, if we're going to use terminology that's been popular in the context of adversarial machine learning for a while, well beyond or well before LLMs became what they are today, or essentially poisoning the AI agent. Instead of poisoning the data that it was trained on, we're poisoning the model's context to get it to do our desired malicious behavior in response to the benign user's activity.
We talk a lot about RAG, retrieval-augmented regeneration. Like, what is it and how does it expand the attack surface for LLM-based systems?
LLMs are trained on a huge amount of data, but their knowledge is always going to be limited to the data that they're trained on and the information that they can extract from it. And I don't mean to kind of understate that. That's a really big deal. That's a pretty cool thing. But if you have kind of proprietary data of yours that is not part of what's going into LLM training, then a model is going to have no way of knowing that information. So some really good examples of this are like product documentation. So if you wanted to make an LLM that was a chatbot for your product, you would probably want to give it access to information about your product that is not part of the public domain. Another example would be if you wanted to develop an internal coding assistant tool and give it access to internal packages that your company has developed. Again, this is information that's not part of the public domain, so it's not going to be part of LLM training sets. There are a couple of ways to give an LLM access to that kind of information. One of them is through fine-tuning. You can actually take the large language model and say, hey, you've already done all of this learning. Now I want you to do a little bit more learning on this extra data that I'm going to pass to you. There are a number of challenges associated with that. One is cost. These large language models are very large, and training them even for little bits can be expensive unless you are a huge company with access to lots and lots of GPUs. So the way that has become more in vogue for how to give an LLM access to this information is through something called retrieval-augmented generation, which is essentially at inference time, in addition to the LLM being able to build responses based on all of the data that's been trained on, you can also give it access to alternative data sources. And it can, for instance, look for answers in those alternative data sources. It wasn't trained on those data sources, but it's using its understanding of human language that's built up through its training process to kind of analyze your company documentation or this internal software package that you've developed and use that information as part of its response. So when we think about how retrieval-augmented generation expands the attack surface for LLM-based systems, we really need to consider first why an attacker would target an LLM-based system. So there's a lot of really good research into attacking open source or publicly available LLMs for the purposes of weaponization. Weaponization here meaning things that we were just talking about trying to get a model to bypass its guardrails so that it can help you do malicious things. You know, in the context of cybersecurity, generally we're talking about, hey, LLM, can you generate a really convincing phishing email for me? Or can you take a look at this software binary and try and identify potential exploits in it? There's a whole other way of attack, or a whole other objective for attacking LLMs that doesn't get talked about as much, where you are not attacking the LLM for the sake of what it already knows as part of its training process. You're attacking an LLM because it represents some proprietary corporate data. Attackers want data. You know, there was a recent large article about 2024, all attacks that they observed in 2024 from Mandiant, now part of Google. And they said that in the attacks that they looked at in 2024, I think 2/3 of them resulted in data exfiltration. You know, when attackers are attacking company environments, it's by and large because they want to exfiltrate data, sometimes on its own, sometimes as part of extortion or ransomware attacks. So attackers want your data. An LLM, through retrieval-augmented generation, has access to your data. It makes a lot of sense that an attacker would then try and target an LLM-based system and get it to exfiltrate data for you. It's essentially, you know, I view it as an efficiency thing. Instead of me as an attacker having to pour through all of this data on my own and figure out what I do and don't want to exfiltrate, I can just ask the LLM system to, hey, give me all of the financial statements from the last year, or please hand over employee personal information. You can get the LLM to do it on your behalf. The other thing here is a well-engineered LLM system should not have access to data that its user does not have access to.
Right.
Lots of AI-based systems or LLM-based systems are not engineered that well. And there are opportunities to potentially escalate privileges and get the LLM-based system to return data that the compromised credentials that you as an attacker have, you might not have access to that data on your own.
Sounds like it makes it even easier for them to get their hands on the data right now with LLMs.
Yeah. I mean, we know that a huge issue in protecting cloud environments is that there are so many possible attack paths that an attacker can take. There's tons of different identities in these environments with things like role-based access control. The environment or the identities become linked to each other in really complicated ways because you can have multiple root identities that are using the same role for different things at the same time. It can be very, very challenging to tease that apart. And we know that there are a ton of cloud services. There are more cloud services being added, it feels like every day. These services are often partially redundant to each other. So from the point at which an attacker has compromised credentials, they have the objective to exfiltrate data, let's say. There are a huge number of different attack paths that they could take to get from where they are to where they want to be. And LLM-based systems that have retrieval-augmented generation enabled represent another attack path that attackers will happily exploit if they think that they can.
So in your experience, what telemetry or model signals are most useful for detecting malicious use?
There are kind of two angles to take here. The gold standard, the approach that's taken in guardrail-based systems like AWS Bedrock has, is prompt monitoring. So thinking about the original LLMs and the attempts to prevent weaponization there, a lot of it is around, hey, user is asking for instructions on how to write a phishing email. This is not something that I want to provide. I'm just going to shut down that prompt immediately. A really interesting thing that I think we'll see a lot more chatter about as ways of attacking LLM models become increasingly complex and sophisticated is output censorship. So I view this as complementary to prompt monitoring, but we have to understand, our systems are never going to be perfect. There's always going to be a world in which an attacker can sufficiently obfuscate their intentions through a prompt injection attack, where my guardrails are not going to be able to tell. We're not going to be able to stop that. But there's the other piece of it. It's not just about, is the model processing this malicious prompt? It's also about, what is the model returning? I think we're going to see a lot more conversation about monitoring the outputs from models as opposed to just the inputs, and making sure that the outputs are in line with whatever guardrails we have set. So yes, we should absolutely be looking for, at the prompt level, an attacker trying to, again, come back to the example of ask an LLM to generate a phishing email for it. But we should also be looking at the outputs from LLM models and asking, hey, does this look like something that we wouldn't want to be returning back to a benign user? And if so, let's block it. For LLM-based systems at scale, there's significant cost and complexity associated with monitoring every single prompt and response, or particularly when you consider the complexity associated. You need what is essentially a language model of its own to look at these prompts and responses to understand if there is anything malicious happening. So when we think about kind of the macro level, looking for malicious usage of LLM-based systems at scale, a lot of that is going to come down to time series and anomalies. So we want to be able to look at questions like, is this LLM in a given session, is this LLM returning a lot more data than it usually does? That might be indicative of some sort of exfiltration attempts. Or did usage of this LLM suddenly increase, or did the sets of IP addresses or ASNs from which we're seeing requests, did that suddenly increase? That might be indication that access keys have been stolen and the LLM is being used as part of an LLM jacking attack, for instance. One other thing that I think is really interesting and important for people to keep in mind is LLMs in the cloud, like through AWS Bedrock, for instance. The intention is that these are back-end tools, not front-end tools, essentially. And what I mean by that is when you look at some of the nuances of AWS Bedrock and how it's architected, it becomes pretty clear that AWS intention is not for users to be interacting directly with the Bedrock model. The system is designed such that they want users to be interacting with some other piece of software that sits in front of the Bedrock model and sends the requests out and then sends the responses back. So when we're considering attack of LLM-based systems, it's important for us to consider not just the models themselves, but are there other software systems, and in particular, are there any public-facing applications that have access to that LLM on the back end? Because that may be where we need to get the telemetry from. So in the case of access key compromise, you may see attackers interacting directly with the Bedrock model, in which case that's where you want to look. But in other circumstances, you may see that front-end application, that might be where you see the strong telemetry signals that indicate potential malicious usage.
And can attackers discover which model or architecture is in use? And if so, how does that inform their strategy?
So generally speaking, yes. I would say attackers can probably relatively easily discover a model family. They may or may not be able to pinpoint down to an individual model within that family. But if you look at the way that those model families respond to certain requests, you can pick up patterns over time. This is essentially like profiling. We in traditional network security, we talk about things like JA3 and JA4 profiling or fingerprinting. You can do a similar sort of thing with LLMs, where if you ask it the same sorts of questions and look at its responses to those questions, you can start to tease apart the model families because they'll tend to respond in different ways. And that has to do with the fact that these model families are trained roughly on the same set of data with the same approaches, and then that will differ from model family to model family. In terms of how that impacts attacker strategy, for most attackers, it's probably not really going to impact strategy. I think every LLM, every model family out there is going to have their own weaknesses. So I don't think we're really going to see much of, or at least given the current state-of-the-art models that are out there, I don't think we're really going to see much of attackers preferentially attacking one type of model family versus another. However, where this can come into play is through shared experiences. And, for every paper you might read or blog post about LLM or model family behavior, you can bet that there are similar posts being circulated around the dark web or available to attackers. So I absolutely would not be surprised if there is a marketplace out there for, hey, you found that you have model family X. We recommend these are the best ways to attack it, versus if you have model family Y, this is going to be a more effective strategy. One of the interesting things right now, though, is that and this is changing kind of day by day, but at least today, I think it is still the case that most publicly used LLM platforms are the ones that are associated with the LLM developers themselves. So, Microsoft has Copilot, OpenAI has ChatGPT, Google has Gemini. Right now, there's still a kind of strong relationship between vendor and model family. And as AI native startups become more and more popular, I think we're going to see more and more cases where a single vendor may be interacting with multiple model families behind the scenes, which is going to muddy the waters quite a bit.
One last question for you. What can data scientists do to better align model design with detection and defense visibility then?
The short answer is work with security experts. I mean, protecting AI systems, protecting LLMs, I think most people would say that that's something that falls outside of the ownership area of a data scientist. But it is still critically important for data scientists to understand the security ramifications of models that they're building or working with. And through partnership with security experts at their companies, for instance, figure out ways to strike the right balance between achieving whatever data science, machine learning, AI objective you're setting out to achieve, while also doing it in a safe way. There are a lot of really interesting novel ways of attacking LLMs. Everything around prompt injection, for instance. That's not something that existed really before LLMs, at least not in the same capacity. And with all of the new around LLMs and generative AI systems, we forget sometimes that they are also software at the end of the day and are therefore vulnerable to all of the same bad software practices that are introduce security risk that non-AI based systems or non-Gen AI systems are vulnerable to also. So I don't think we have any reason to believe at this point in time that there's any particular LLM model family or model architecture that is intrinsically safer than another one is. And I would be highly surprised if that ever ends up being the case. But as anytime a data scientist is producing something that is either directly being interacted with by end users or is the backend for a system that is being directly interacted with by end users, it's important to consider the security ramifications. It's important to consider what are the things we can and should do to help keep this system safe, help keep the data behind the system safe, and help keep our users safe as well. One particular example that comes to mind, this is from before generative AI became the thing that it was today, but the field of adversarial machine learning has been around for quite a long time. And there's a really wonderful study posted probably 5 years ago or so, 5 or 6 years ago, about model theft. So model theft is essentially, I'm a bad guy, I have access to a machine learning model. I'm going to send a bunch of requests to that model, get the responses back, and essentially through that process, I'm building up my own labeled training set that I can use to train a model that should behave very similar to this other model. I'm stealing this model through reconstructing it based off requests and responses. And this study found that if the model returns kind of its full thoughts, so these are all of the different classes that I considered between, and these are the scores that I gave to each of these classes, and then I ended up picking this one class that had the highest score, versus the model just saying, class A, class C, class B, just returning that end classification. By restricting the amount of information that the model returns, you make model theft like 4 orders of magnitude harder in terms of the number of queries that an attacker needs to send to be able to reconstruct that model. It'll be interesting to see how pieces of kind of pre-LLM adversarial machine learning research, how that begins to infiltrate Gen AI systems more. One of the reasons why Gen AI systems are so popular is because they can give these verbose responses. So by just limiting the amount of information that a Gen AI system is returning, you're negatively impacting the end user experience. But we also don't want to give more information than is needed for the end user. So I think it'll be interesting to see as Gen AI models, Gen AI systems continue to be more ingrained in our day-to-day lives, how we can protect data through striking the right balance between delivering the end user the information that they want and expect, while also not delivering more than that and putting the models at risk.
Thank you, Zach, for your valuable insights. That was very much interesting. Learned a lot.
Thank you, Lucie. Happy to share.
So that wraps up this episode of the Threat Briefing podcast. If you found this conversation valuable, you can check out our latest product briefing episode about, how we detect attacker abuse in Microsoft Copilot for M365. In that one, we break down how our platform is catching attackers abusing Copilot in real time. Be sure to subscribe, revisit past episodes, and stay tuned. We'll be back soon with more insights from a security researcher perspective into how attackers are targeting Gen AI infrastructure across platforms like AWS Bedrock that we talked about in this episode. Thanks for listening. See ya.
Bye.